This is Lesson 1 in our Calculus 2 series, Inverse Functions. Recall that y is a function of x if for each x value there is only one corresponding y value. Let's take a look at the graphs here and see if they are graphs of functions. Let's take a look at the circle. For each x value, is there only one corresponding y value? Let's take a look at the point 4, 3. Notice the point 4, -3 is also on this graph. So for the same x value of 4, we have two different y values. That tells us that the circle is not a function. Or more specifically, y is not a function of x. An easy way that we can determine if a graph is a graph of a function is if it passes the vertical line test. Notice that if we take a vertical line at x equals 4, it's going to hit the graph twice, telling us that we have two different y values for the same x value. The vertical line test says any vertical line should hit the graph at most once if the graph represents a function. So any vertical line that we pass could only hit the graph at most once if it's the graph of a function. So here the graph fails the vertical line test. Now let's take a look at y equals x squared. Again, we want to see if y is a function of x. So we want to verify that for each x there is only one corresponding y value. Using the vertical line test, we can see that any vertical line will hit this graph once, saying there is only one y value for that corresponding x value. So here we have y is a function of x. And same thing for y equals x to the third. This will also pass the vertical line test. Any vertical line here will hit the graph at most once, and so y is a function of x. Now let's talk about what it means to be a one-to-one function. To be a one-to-one function, it first has to be a function, so that says for each x value there's only one corresponding y value. But then to be a one-to-one function, the reverse is also true. For each y value, there is only one corresponding x value. For each y value, there is only one corresponding x value. So now we know that these two are functions. We just showed that. Let's see if they are also one-to-one. We know the point 1, 1 is on y equals x squared. Also, -1, 1 is on y equals x squared. That tells us we have two x values that share the same y value. But a one-to-one function says that each y value only has one x value. So here we found y equals 1 has two x values. And so this is not a one-to-one function. And you could see that I used a horizontal line to show that for that y value of 1, we had two x values on this curve. That is the horizontal line test. To see if a function is one-to-one, any horizontal line should hit the graph at most once if the function is one-to-one. So we already know that it's a function, we just want to see if it's a one-to-one function, we use the horizontal line test. Because this graph has at least one horizontal line that hits the graph more than once, we know it's not a one-to-one function. But notice for y equals x to the third, any horizontal line is going to hit the graph at most once. Even our x-axis, y equals 0, hits only at the origin. So y equals x to the third is a one-to-one function. It passes the horizontal line test. Now notice for a function that's continuous on the whole real line, if it's going to be one-to-one, it would have to be strictly increasing or strictly decreasing. So even if we didn't have the graph of y equals x to the third, we could use the methods of calculus to show that this is a strictly increasing function on the entire real line. And therefore we know that no two x values can share the same y value. So for y equals x to the third, we could take a look at y prime that's 3x squared. We know that 3x squared is equal to 0 only when x is equal to 0. And for every other x value, 3x squared is positive. So that says this graph increases. It has one point at which the slope is horizontal and then continues to increase. That makes this graph strictly increasing on the entire real line. And that will tell us that our function is one-to-one. Now, the nice thing about one-to-one functions is that if we switch the role of x and y, we still get a function. And that we're going to call the inverse function. So let's start with y equals x to the third, and let's solve for x. So we do that by taking each side to the 1/3 power, and that gives us x is equal to y to the 1/3. Now, I didn't switch the roles of x and y yet, all I did was solve for x. Now I want to switch the roles of x and y. So I'm going to take this y, change it to x, take this x, change it to y, and now we have y equals x to the 1/3. This is the inverse function for y equals x to the third. And in the notation of inverse functions, we can say f of x equals x to the third, and then f inverse of x is equal to x to the 1/3. We read this as f inverse of x, and that's a superscript here of a -1. So now we have f and its inverse. How is this useful to us? Well, let's take a look at the properties of inverse functions. Essentially, inverse functions undo each other. So for any f and f inverse, when you compose them in either order, you get back what you started with. And we'll take a look at that in just a second. The other property that's important to us about inverse functions is the one-to-one pairing of points. And we saw this a little bit as we were talking about the horizontal line test. But we'll take a closer look at the graphs of these two functions in just a second. Essentially, we're saying if we know that f of 2 is equal to 8, then we know that f inverse of 8 is equal to 2. It's like a monogamous relationship between the x and y pairs. Let's take a look at the composition property for f of x equals x to the third and its inverse function, f inverse of x equals x to the 1/3. And let's take a look at f inverse of f of 2. So first we're plugging 2 into f, and then we're taking that result and plugging it into f inverse. Now the defining property about inverse functions is that they undo each other, so we should end up with whatever we plugged in. We should end up with a 2. But let's take a look at that for these functions here. F of 2 is 2 to the third. Here's our f of x. F of 2 is 2 to the third. So we're looking at f inverse of 8. So that is 8 to the 1/3, which is 2. So whatever f does to 2, f inverse is going to undo and give you back your original 2. That's always going to happen with inverse functions. We could compose in the other direction as well. Let's take a look at f of f inverse of -27. F inverse of -27 is -27 to the 1/3 power. That's going to be -3. So now we have f of -3. Well, that's going to be -3 to the 3rd power. That's -27. So whatever f inverse did to the -27, f undid and gave us back that same number. And in general for these functions, for any x value, we have f of f inverse of x is equal to f of x to the 1/3. So that's x to the 1/3 taken to the 3rd power, which gives us back x. F inverse of f of x is f inverse of x to the 3rd. So that's x to the 3rd taken to the 1/3 power. Again, that gives us back x. Now let's take a look at the other property, the one-to-one pairing of points. Well, here's our graph of f of x equals x to the 3rd. That's the black graph here. And notice that we have, for example, the point 2, 8 on that graph. That tells us that on the inverse functions graph, we're going to have 8, 2. Because remember, the inverse function switches the roles of x and y. So on the graph of f inverse of x, we have 8, 2. And so for every point that we have on the graph of y equals f of x, we're going to switch the x and y coordinates, and that's going to give us the graph of y equals f inverse of x. And so the graphs of f and f inverse are going to be reflections of one another through the line y equals x. And that's always going to happen for graphs of inverse functions. Now remember that we said one-to-one functions are the ones that have inverse functions. So let's take a look at this example. Does f of x have an inverse? F of x is equal to negative 2x to the third minus x plus 7. If we're asking, does it have an inverse, then we're asking, is it one-to-one? Now earlier, the way that we showed a function was one-to-one was by using the horizontal line test. But this is not going to be an easy graph to sketch. We would need to use the methods of calculus to sketch this graph. So instead of going through all of those details to get the sketch, let's see if we can show that this graph is one-to-one without actually getting the sketch. Earlier we showed that for y equals x to the third, we showed it was strictly increasing on its domain, and therefore it was a one-to-one function. So let's see if we can show that this function, whose domain we know is the entire real line, let's see if we can show that this function is either strictly increasing or strictly decreasing. If we can show that, then we know the function is one-to-one, and then we know that it has an inverse. So we'll take the derivative here. That's negative 6x squared minus 1. By factoring out the negative, we can see that this is always going to be negative. We have 6x squared plus 1. We know that will be strictly greater than 0 for all x. And so with a negative, we've got f prime less than 0 on the entire real line. That says that f of x is strictly decreasing on its domain, and f is then one-to-one and has an inverse. So now we've answered the question. The question was, does this function have an inverse? And we found an answer, yes it does. But notice, if we were going to try to solve for the inverse function, we would have to solve this equation for x. Right? To find the inverse function, we set y equal to this function, we solve for x, and then switch x and y and continue, but we can't solve for x here. So we can't explicitly find f inverse here. We can, however, find f inverse evaluated at particular points. For example, we know that f of 0 is equal to 7. Therefore, f inverse of 7 is equal to 0. Because we know this function has an inverse, therefore we know we have this unique pairing of points. If f of 0 is equal to 7, f inverse of 7 is equal to 0. Similarly, we know that f of 1 is equal to 4. Well, that tells us that f inverse of 4 is equal to 1. So although we can't explicitly write down the function f inverse of x, we do have some evaluations based on the original function evaluations. And if we take a look at the sketch of f of x, we will be able to get a sketch of f inverse by taking its reflection through y equals x. For example, we know that 0, 7 is on the original function. That means 7, 0 is on the inverse function. 1, 4 is on the original function, so 4, 1 is on the graph of the inverse function. So this is our graph of f of x, and this is the inverse function graph. And they are reflections through the line y equals x. Now, what if f is not one-to-one? Can it have an inverse? Well, it can't have an inverse on its entire domain, but if we restrict the domain of that function so that it is one-to-one on that domain, then it will have an inverse function. For example, if we take a look at f of x equals x squared plus 4, we can see that on its domain of the entire real line, it is not one-to-one. It does not pass the horizontal line test. However, if we restrict to x greater than or equal to 0, then we're only talking about this half of the graph. And then yes, in that case, f is one-to-one, and it will have an inverse. So we'll set y equal to x squared plus 4, and we'll solve for x. So y minus 4 is equal to x squared. Now, when we take the square root, we know that we need mathematically to put the plus or minus. But because here we know that x must be greater than or equal to 0, we know that we're only choosing the positive here because x is greater than or equal to 0. So that gives us a defined x equals radical y minus 4. So now we can switch x and y. Y is equal to radical x minus 4, and that is our inverse function. So taking a look at the graphs, we have f of x equals x squared plus 4 for x greater than or equal to 0. That's this part of the parabola. And its inverse function, f inverse of x, is equal to radical x minus 4. Now let's take a look at the domain and range for each of these functions. For f of x equals x squared plus 4, for x greater than or equal to 0, well, here's the domain. It's that restriction, right? X greater than or equal to 0. Or we could write that as 0 to infinity, closed on 0. The range for this function has y values greater than or equal to 4. Or we can write that as 4 to infinity, closed on 4. Now let's take a look at the domain and range for f inverse. The domain here is x values greater than or equal to 4, or 4 to infinity. And the range is y values greater than or equal to 0, or 0 to infinity. Notice what happened here. The domain we had for f is now the range for f inverse. And the range we had for f is now the domain for f inverse. And that makes sense because to get the inverse function, we switch the roles of x and y. So because we switch the roles of x and y, the domain of f of x is equal to the range of f inverse of x. And the range of f of x is equal to the domain of f inverse of x. And that's always going to happen for any pair of inverse functions. Now let's take a look at the calculus of inverse functions. Suppose f and g are inverse functions. In other words, g of x is f inverse of x. And we know f prime. We know the derivative of f. We want to find the derivative of g, or f inverse prime of x. That's what we're looking for. We've got a pair of inverse functions. We know the derivative of one of them. We want to find the derivative of the other. So what we're going to do right now is talk about a relationship between the derivatives of inverse functions. Now we know that because they're inverse functions, when we compose them, we get back x. So let's take the derivative of this equation with respect to x. On the left-hand side, we use the chain rule, and we get f prime of g of x times g prime of x. On the right-hand side, we just get 1. This tells us g prime of x is 1 over f prime of g of x. We just divide by f prime of g of x here. So now we have a formula for finding g prime based on f prime and g. Let's show that this relationship holds for the pair of inverse functions we had above. F of x is equal to x to the third, and g of x is equal to x to the 1/3. So we know f prime, and we're going to pretend we don't know g prime, and we're going to use this formula and show that we get what we expected. So f prime of x is 3x squared. So g prime of x, using the formula above, is equal to 1 over f prime of g of x. So f prime is 3x squared. We want to plug g into f prime. So we have x to the 1/3 plugged in here. That gives us 3 x to the 1/3 quantity squared. So we've got 1 over 3 x to the 2/3. Okay, now let's check our derivative the straightforward way for g. g is equal to x to the 1/3, so its derivative is going to be 1/3 x to the negative 2/3, and yes, that's the same. This relationship between the derivatives of inverse functions is going to help us as we talk about exponential and log functions, and as we talk about trig functions and their inverse functions. Now, when I used the chain rule up here, I was assuming that f and g were both differentiable functions. But let's take a look at this theorem for a more formal statement of the relationship between the derivatives of inverse functions. If f is a one-to-one differentiable function with inverse f inverse, and if f prime of f inverse of a is not 0, then f inverse is differentiable at a, and f inverse prime of a is equal to 1 over f prime of f inverse of a. So this is the same relationship that we developed above, but here we're not making any assumptions about the differentiability on f inverse. This theorem is actually giving us the differentiability of f inverse at a, and the proof uses the definition of the derivative. I'm not going to show the proof here, but you can find that in many textbooks. Let's take a look at this example. F of x is equal to x to the 5th minus x to the 3rd plus 2x. We're asked to find f inverse prime of 2. Now, they didn't ask us to show that f inverse is differentiable. They didn't ask us to show that f inverse exists. They just said find f inverse prime of 2. So for this type of problem, if you saw this on your homework or an exam, we can assume that f inverse exists and is differentiable at 2, and we just need to worry about computing it. In this case, though, if you did want to show existence here, you could show that f of x is strictly increasing or decreasing, which would give us that f is 1-to-1 and has an inverse. And then by showing it strictly increasing or decreasing, we would get that f prime is not 0 at this point, and so we'd have the existence of f inverse prime of a. But again, for this type of problem, I think it's okay to assume that it exists and just do the computation. Now they're asking for f inverse prime of 2. And the more straightforward way might be to find f inverse. But if you notice, finding f inverse would require solving y equals x to the 5th minus x to the 3rd plus 2x, solving that for x. And we can't do that. But notice that they didn't ask us for f inverse. They wanted f inverse prime. So they want us to make use of the relationship that we have here. So f inverse prime of x is 1 over f prime of f inverse of x. We want to find f inverse prime of 2. So that's going to be 1 over f prime of f inverse of 2. So we need to figure out what's f inverse of 2, and then what's f prime of that value. What is f inverse of 2? F inverse of 2 is the x value when y is equal to 2 on y equals f of x. It's the x value corresponding to y equals 2. Because remember, if the point AB is on y equals f of x, then the point BA is on y equals f inverse. In this case, we have f of A is equal to B, and here we have f inverse of B is equal to A. So if we're looking for f inverse of 2, that's an A value such that f of A is equal to 2. Or we can say it's an x value such that f of x is equal to 2. Here's our function f of x. We set that equal to 2, and we want to solve for x. But you might be thinking, this is the same problem we had before. We can't solve for x. Well, in these kinds of problems, it's going to be trial and error, and it's always going to be something easy. So try x equals 0 or x is equal to plus or minus 1. It's usually one of these x values. In this case, we see when x is equal to 1, we get f of x is equal to 2. So f of 1 is equal to 2, and 1 is equal to f inverse of 2. So that tells us we can put a 1 in here. Now we need f prime of 1. Okay, well here's f of x, so here's f prime, plug in 1, we get 4. So 1/4 is the derivative we're looking for. And with this, we'll conclude our lesson on inverse functions.